In this video, we are going to discuss the test of significance of difference between the means of two large samples drawn from the same population or two different populations with either same mean and standard deviation or different means and standard deviations. So let's discuss this test. So suppose x1 bar and x2 bar be the means of two large samples of sizes n1 and n2 respectively drawn from the two populations with the same mean mu and variances sigma 1 and sigma 2 square respectively. Here mean of the population need not be the same, the means may be different. Then x1 bar follows the normal distribution with mean mu and standard deviation sigma 1 upon under root n1. This we have seen in the test of significance of difference between sample mean and the population mean. And similarly the second mean will follow normal distribution with mean mu and standard deviation sigma 2 upon root n2. So expectation of x1 bar minus x2 bar is equal to expectation of x1 minus expectation of x2 bar. Here expectation of x1 bar is mu and expectation of x2 bar is also mu. Therefore this will be 0. But in practical these two may not be the same. Here we may have mu1 and mu2. That means means of the two populations may be different. But here we have assumed that they are same. That's why this is equal to 0. In case means are different, then we will get result like this, mu1 minus mu2. Now variance of the difference of the means is equal to variance of x1 bar plus variance of x2 bar, which is sigma 1 square upon n1 plus sigma 2 square upon n2. So x1 bar minus x2 bar follows a normal distribution with mean 0 and standard deviation under root sigma 1 square upon n1 plus sigma 2 square upon n2. Therefore the test statistic becomes, using this formula, z equal to sample statistic minus expectation of that sample statistic upon standard error of the sample statistic. So here expectation of theta we have found that is 0 and standard error of theta means standard error of the difference of means, which we have obtained as sigma 1 square upon n1 plus sigma 2 square upon n2. So depending on the situation where sigma 1 not equal to sigma 2, that means the population standard deviations are not equal, then we find this formula of the test statistic z. Similarly if sigma 1 equal to sigma 2, that means the standard deviations of the populations are the same, then we find this formula of test statistic. And in case sigma 1 not equal to sigma 2 and they are not known, then you can use the sample standard deviations in place of sigma 1 and sigma 2. And in case sigma 1 and sigma 2 are equal but not known, that means the samples have been drawn from the same population, then you can use this formula. Where sigma is not known, then an unbiased estimate of sigma can be obtained using this formula. So when we substitute sigma square here in this formula, we get x1 bar minus x2 upon s1 square upon n2 plus s2 square upon n1. So this formula is in case where sigma 1 equal to sigma 2 but it is not known, then we have to use this formula. And this formula is applicable when sigma 1 equal to sigma 2, that means the samples have been drawn from the same population or the two different populations with same standard deviation sigma and it is known, then we have to use this formula. So these are the formulae for the test statistic. Whichever is applicable you should apply, and other things will remain the same. That means the null hypothesis and alternative hypothesis and level of significance and critical values, those values will remain the same. So let's take an example. In a certain factory there are two independent processes manufacturing the same item. The average weight in a sample of 250 items produced from one process is found to be 120 grams with a standard deviation of 12 grams, while the corresponding figures in the sample of 400 items from the other process are 124 grams and 14 grams. Obtain the standard error of difference between the two sample means. Is the difference significant? Take level of significance as 1%. So if we note down all the given figures, we find that the sample size of the first sample is 250, sample size of the second sample is 400, mean of the first sample is 120, mean of the second sample is 124, standard deviation of the first sample is 12, standard deviation of the second sample is 14. Now we have to find the standard error of difference between the two means. So his standard error of difference between the two means is equal to s1 square upon n1 plus s2 square upon n2. Here we have two different populations. One population is with the process 1 and the other population is with the process 2. Therefore we have used this formula s1 square upon n1 plus s2 square upon n2. Here sigma 1 and sigma 2 are not known, therefore we have taken s1 square and s2 square in place of sigma 1 square and sigma 2 square. So we find that the standard error of difference between the two means is 1.0325. Now to test whether this difference is significant or not, we set the null hypothesis where x1 bar equal to x2 bar. That means the difference between the average weights is not significant. That means these two are the same, and the difference which we see here in x1 bar and x2 bar is due to fluctuation of sampling. That means due to sample sizes. Here we have taken first sample of size 250 and second sample of size 400. So this difference is due to these two difference between the sample sizes. So in H0 we assume that there is no difference between the two means, and the difference, if any, is due to fluctuation of sample size. But in H1 we assume that x1 bar is not equal to x2 bar. That means the difference is actual and not due to the fluctuation of sample size. Here alpha level of significance is 0.01 and the corresponding critical value of z corresponding to two-tailed test is 2.58. That means we have to apply the two-tailed test. So this is the value of z corresponding to 1% level of significance for two-tailed test. So here the acceptance region is between minus 2.58 and plus 2.58, and this is the 1% area on either sides. So here, since the two samples have been drawn from the two different populations with unknown standard deviations, therefore we have to use this formula, and the corresponding value of z is minus 3.874. So this value of minus 3.784 falls in the critical region. If you see this is minus 2.58. This is the critical region, and this value falls somewhere here. So H0 is rejected and H1 is accepted. That means the difference between the average weights is significant. Take another example. A brochure inviting subscription for a new diet program states that the participants are expected to lose over 22 points in 5 weeks. Suppose that from the data of the 5-week weight losses of 56 male participants, the sample mean and the sample standard deviations are found to be 24.25 and 10.2 respectively, and that of 50 female participants to be 20.25 and 9.7 respectively. Can it be concluded that the program is more effective for male? Take level of significance 2%. So here if we note down all the figures, then we find that the mean of the male, we find that x1 bar equal to 24.25, which is weight loss of men, standard deviation to 10.2, n1 56, that means sample size of male. X2 bar equal to 20.25, that means the weight loss of females. S2 standard deviations of the weight loss 9.7, N2 sample size of the females. Here we set H0 as x1 bar equal to x2 bar, that means the program is equally effective for male and female. That means the claim of the brochure is true. And H1 x1 bar greater than x2 bar, that means weight loss in men is greater than that of in female. Here we set H1 as x1 bar greater than x2 bar, that means the program is more effective for male. Now here level of significance is 0.02, that means the critical value at corresponding to 0.02 is 2.055. Right tail test. So here we have to apply the right tail test, because here alternative hypothesis is x1 bar greater than x2 bar. So this value is 2.055 corresponding to 2% level of significance. So this area is 2% and this is the region of acceptance. Critical region is this. Now here the two samples have been drawn from the same population. The population is the population which has been given the diet program, and the two samples have been drawn from the same population, and the standard deviation sigma is unknown. Therefore, we use this formula S1 square upon N2 plus S2 square upon N1 for standard error of the difference between the two means. So here computed value of Z is 2.063. 2.063 falls in the critical region. Therefore H0 is rejected. That means the program is more effective for male. Take another example. A company has developed a new battery. The engineer in charge claims that the new battery will have better performance than that of the old batteries. To test the claim, the company selects a simple random sample of 90 old batteries and 65 new batteries. The old batteries ran continuously for 190 minutes with a standard deviation of 32 minutes. The new battery is 200 minutes with a standard deviation of 45 minutes. Test the engineer's claim at 5% level of significance. So again, if we note down the given figures or data, we find that sample size of the old batteries is 90 and the mean running time is 190 minutes, standard deviation 32 minutes, N2 the sample size of the new battery is 65, X2 bar mean time or mean running time of the new battery is 200 minutes and standard deviation is 45 minutes. So here what is H0? H0 means x1 bar equal to x2 bar. That means the old and the new batteries have the same performances. There is no difference between the performances of the old batteries and new batteries. Here H1 is the old batteries have less average running time than that of the new batteries. That means the new battery has better performance than that of old battery. And here we see that alpha is 0.05 and here we have to test the claim at 5% level of significance. It is left tail test and the corresponding value of of Z at 0.05 is, this is minus 0.645. So this is the critical region and this is the region of acceptance. And since the samples have been taken from two different populations, so here the populations are different because the first sample has been taken from the population of old batteries and the second sample is taken from the population of new batteries. Therefore, two populations are different and their sigma or standard deviations are unknown. Therefore, we have to use this formula. So here computed value of Z is minus 1.5334. So if we compare this value, then we find that this is minus 1.645. This computed value of Z falls in this region. Therefore, H0 is accepted and H1 is rejected. That means the engineer's claims is not true. There is no difference between the running times of old batteries and the new batteries. So this was the test of significance of the difference between the means of two large samples. I hope you understood what I have told you. Thank you very much.